Right, so in 7.3, we're going to be focusing on proving or disproving identities. So the first thing we want to talk about is how we disprove an identity. So to disprove an identity, that is to show that something is not an identity, we must find one input that makes the equation false. This input is called a counterexample. So just to remind us, an identity is an equation that is true for every variable in the domain. So to show that something is not an identity, we only have to find one that doesn't work. Because if it has to work for every, the negation of every x working is there is at least one that doesn't work. So let's start with example number 1, which says show that sine squared x minus sine x cosine x equals 1 minus cosine squared x minus sine 2x is not an identity. So if we start picking some values to check to see if they're an identity, so for instance, if I pick x equal to 0, and I put 0 into this equation, well, that gives me sine squared of 0 minus sine 0 cosine 0. And we want to know, does that equal 1 minus cosine squared of 0 minus the sine of 2 times 0? And we start simplifying, and we know that the sine of 0 is 0, so that's 0. That's going to be 0. So then on the left side, we have 0 minus 0, which is 0. And the cosine of 0 is 1, and 1 squared is going to be 1, so 1 minus 1 is 0. So for x equals 0, that's true. But showing that it works for one value of x also doesn't make it an identity, because it has to work for every value. So now this time, if we try pi over 6, we get the sine of pi over 6 squared minus the sine of pi over 6 times the cosine of pi over 6. And we want to know, does that equal 1 minus the cosine squared of pi over 6 minus the sine of 2 times pi over 6, and 2 times pi over 6 is going to be pi over 3. So now we need to start simplifying. If we look on our unit circle, the sine of pi divided by 6 is 1/2, so this is going to be 1/2 squared minus 1/2, and the cosine of pi over 6 is going to be the square root of 3 over 2, and we want to know, does that equal to 1 minus the cosine of pi over 6 is still square root of 3 over 2 squared minus the sine of pi over 3, and the sine of pi over 3 is going to be the square root of 3 over 2. And when we start simplifying, 1/2 squared is 1/4 minus the square root of 3 over 4. And we want to know, does that equal to 1 minus square root of 3 over 2 is 3/4 minus the square root of 3 over 2. And we get our common denominator by making this a fraction over 1. And then we multiply the top and the bottom of this by 4 over 4 and this by 2 over 2. And we simplify, so we get 1 minus the square root of 3 over 4. And on the right side, we have 4 minus 3, which is 1 minus, but then we have 2 times the square root of 3, so that's 2 square roots of 3 all over 4. And these two things are not equal. So that tells us that pi over 6 is a counterexample. And pi over 6, and So the equation is not an identity. So to show something's not an identity, we have to find at least one value that doesn't work. So when I guessed pi or x equals 0, we got something that was true. So that's a solution to the equation, but then we discovered it doesn't work for every x. In general, when we're trying to find counterexamples, we don't want to pick any angles whose terminal side is on an axis. The reason for that is when we are on an axis, either sine or cosine is going to be equal to 0. And what happened in this example is since sine of 0 is 0, multiplication by 0 makes anything equal to 0. And so that often will simplify things down into true statements. Not always, but more so than if you pick other random elements. All right. So let's transition away from counterexamples and talk about this in the positive sense. So when we're trying to prove some identities, we have one warning and then a couple of tips to help us prove trigonometric identities. So the first thing is we want to take note of as a warning that we can't use the properties of equations to prove identities. Because until we prove an identity, we don't know that it is a true equation. So it would be circular logic to use properties of equations on something that we haven't proven is an equation yet. So our 4 tips are: try starting with the side of the equation that looks more complicated. In general, in mathematics, it is easier to simplify something. What that means is it's easier to take something that is complicated and make it more simple than it is to take something that is simple and make it more complicated. Not always the case, but in general, that is true. Even though these are trigonometric identities, oftentimes a bulk of what we're going to do is use algebra. So C, convert everything to sines and cosines. And to build on that, sometimes it's beneficial to look at what we have on one side of the equation, because since we're trying to make an identity, we want to make both sides the same. So look at what we have and what we want and try to turn what you have into what you want. And so D sounds a little bit silly, which says just try something. But the most common thing I see when people get stuck on trigonometric identities is they just sit there and stare at it and say, I don't know what to do. Well, oftentimes we don't. So just try something and see what happens. So I really implore you to think about this kind of like the scientific process, right? Proving trigonometric identities is like doing an experiment. Sometimes you just have to do something, make some observations, find out what went wrong, but also what went well, and then go back and start over and try again using what you learned from the first attempt. And it is not uncommon to have to try an identity several times before you get the right path. Also on that, when I say the right path, I'm going to use that rather loosely because there are an infinite number of ways to get from A to B. So if you're working with someone else or collaborating with someone, they may prove an identity in a different way than you do. But if they use valid algebra and valid trigonometric identities and get to the same ending place, then both of you can be correct. So there's not a one way to do any of these problems. All right. So the best way to learn how to do trigonometric identities is just to do trigonometric identities. So example 2. Let's establish the identity 9 secant squared theta minus 5 tangent squared theta is equal to 5 plus 4 secant squared theta. All right, so we want to prove this identity, and we notice that on the left-hand side, we have both secants and tangents, And on the right-hand side, we only have secants and constants. So the first thing I'm going to do is take a look at my identity sheet. So do I have an identity on here that I can use that will turn tangents into secants and constants? And I do. It's one of the Pythagorean identities right here, but I'm going to have to do a little algebra on it first, because I have 1 plus tangent squared x equals secant squared, which isn't exactly quite what we want. So when proving trigonometric identities, similar to when I was simplifying, I'm going to divide my page in half and do my 2 columns. So on one side, I'm going to write the actual thing I'm working on. So I have 9 secant squared theta minus 5 tangent squared theta is equal to 5 plus 4 secant squared theta. So then I'm going to use the identity 1 plus tangent squared theta is equal to secant squared theta. But before I can use it, I need to subtract 1 from both sides. So if I minus 1 from both sides, it leaves me with the identity tangent squared theta is equal to secant squared theta take away 1. So I'm going to use this identity on my tangent squared of theta. So then that gives me 9 secant squared theta minus 5 times secant squared theta minus 1 is equal to 5 plus 4 secant squared theta. So the next thing I'm going to do is just algebra, which is distribute. So if I distribute my 5 into my parentheses, I get 9 secant squared theta minus 5 secant squared theta minus 5 times negative 1 is positive 5 is equal to 5 plus 4 secant squared theta. And lastly, we'll just collect our like terms. And so we have our secants that we collect up. So 9 secant squared minus 5 secant squared is 4 secant squared theta plus 5 is equal to 5 plus 4 secant squared theta. And we're done. Which is the identity that we wanted. So when proving trigonometric identities, we will use the identities from our identity sheet, plus we will use any algebra or anything else that we may need. All right, so let's take a look at our next identity. So, we wish to establish the identity 1 plus sine theta over 1 minus sine theta is equal to secant theta plus tangent theta squared. All right, so looking back at our hints, it says try starting with the side of the equation that looks more complicated. Well, that's kind of a toss-up here because I have a fraction on one side and I have a binomial on the other side. Well, let's go ahead and multiply out the right-hand side. So we start with our identity, which is, or with our equation, 1 plus sine theta over 1 minus sine theta is equal to secant theta plus tangent theta squared. And let's go ahead and distribute out the right-hand side. So then my left-hand side stays the same, so 1 plus sine theta all over 1 minus sine theta is equal to, and if I were to distribute out this side, secant times secant is secant squared theta, secant times tangent plus secant times tangent is 2 secant theta tangent theta, and then tangent times tangent is tangent squared theta. So now we need to continue trying to do this. So now we have sines only on the left side, and on the right side we have secants and tangents. So one of our things was to convert everything to sines and cosines. So let's try that here. So let's rewrite as sines and cosines. So secant is 1 over cosine. We're going to have 1 plus sine theta all over 1 minus sine theta is equal to, we're going to have 1 over cosine squared theta plus 2. Secant is still cosine, and tangent is sine over cosine, so it's going to be 2 sine theta over cosine squared theta. And then lastly, tangent is going to be sine squared theta over cosine squared theta. So now, on the right-hand side, they all have a common denominator of cosine theta. So let's go ahead and factor and combine. So in the numerator, we have something of the form 1 plus 2x plus 2x, or plus x squared. So when we factor that, in the numerator, we're going to end up with sine x plus 1 over cosine squared, sorry, it shouldn't be an x, it should be theta, because we're using the variable theta. Sine theta plus 1 over cosine because this factors into 1 plus x squared. And then our left-hand side stays exactly the same. 1 plus sine theta over 1 minus sine theta. So since the left-hand side has only sines in it, let's rewrite cosine squared theta as 1 minus sine squared theta. And then we have 1 plus sine theta all over 1 minus sine theta is equal to sine theta plus 1 squared over 1 minus sine squared theta. So now finally, this is the difference of squares. So 1 minus x squared factors into 1 minus x times 1 plus x. And finally we get 1 plus sine theta over 1 minus sine theta is equal to sine theta plus 1 squared over 1 minus sine theta times 1 plus sine theta. So finally, that reduces, and then we're done. Because now we have 1 plus sine theta over 1 minus sine theta, and here we have 1 plus sine theta over 1 minus sine theta. All right. All right, so to work this u-trie, we're going to convert our secants to 1 over cosine. So we have the equation. So secant t take away 1 over t secant t equals 1 minus cosine t all over t. So we're going to use the definition of secant t is 1 over cosine t. So then if I replace all of my secant t's with 1 over cosine t, I get 1 over cosine t minus 1 over t times 1 over cosine t. And I want to show that that's equal to 1 minus cosine t over t. So then we're going to clear the fractions by multiplying by the LCD of all fractions. And it's worth noting at this point that it's also the same as inverting and multiplying. You're going to get the same result if you do that. So there's more than one way to do this. So we multiply the top by cosine t, and we multiply the top by cosine t. And if we distribute that into our parentheses, we end up with cosine over cosine, which reduces to 1, times 1, so minus cosine t, and then in the denominator they reduce out all over t, equals 1 minus cosine t over t, and we're done. And if you did the invert and multiply, you end up with the same thing when you distribute. So either way, we're going to get the same thing, which is our identity. All right, so let's keep going. So example 4 Same instructions. We want to establish this identity. Well, thinking back to our list of things that we're supposed to try, the left-hand side looks much more complicated than the right-hand side. So to get started, the first thing we're going to want to do is expand everything out and simplify. So for the first bit, we're just going to use algebra to expand everything. So sine theta plus cosine theta squared, if we multiply out that binomial, we're going to end up with sine squared theta plus 2 sine theta cosine theta plus cosine squared theta. And if we multiply out the second one, we're going to get the same thing, except for it's going to be negative in the middle. So we're going to end up with plus sine squared theta minus 2 sine theta cosine theta plus cosine squared theta. I should probably color code these because that's not entirely clear what's happening. Because this thing is big enough that I need to write it on two separate lines. All right. So that's just these two things. So then when we collect our like terms, the thing that's interesting is in the middle. Those reduce out. And then sine squared theta plus sine squared theta is 2 sine squared theta. Cosine squared theta plus cosine squared theta is 2 cosine squared theta equals, and we want to show that all of this was equal to 2. So now we're going to factor out the GCF. And our GCF is 2, and that leaves behind sine squared theta plus cosine squared theta equals 2. And then finally, this guy should look a little bit familiar. That's the Pythagorean identity. And sine squared theta plus cosine squared theta is equal to 1. So that gives us 2 times 1, which equals 2. Which is exactly what we wish to show. So the bulk of this one was actually doing algebra. And then we did just a teeny bit of trigonometry. All right, so the next problem, you might be saying, well, wait a minute, didn't we do that one just a few questions ago? And you are correct. We did do this. We'll go back and take a look at it, but this time the Hint Ninja has showed up to give us a hint on a different way to do this. And what the Hint Ninja is really going to be teaching us here, or telling us about, is a technique that is often helpful when trying to prove trigonometric identities. So we want to establish the identity, and let's go back and take a look. So this was what we did in example number 3. Last time, in example 3, we expanded the right-hand side and turned it into the left-hand side. The Hint Ninja says, well, let's establish the identity, but it wants us to use the conjugate. So if you remember, the conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. That is, you change the sign in the middle. So if we were to look at 1 minus sine theta, the conjugate of 1 minus sine theta is 1 plus sine theta. So the Hint Ninja wants us to use the conjugate. And we're going to use it on the left-hand side. So we start with 1 plus sine theta over 1 minus sine theta. And then our conjugate will multiply the top and the bottom by 1 plus sine theta. And 1 plus sine theta. And we want to show that that is equal to secant theta plus tangent theta squared. So here we're just going to use the conjugate. So in the numerator, 1 plus sine theta times 1 plus sine theta is 1 plus sine theta squared. And 1 minus sine theta plus 1, or times 1 plus sine theta, is the difference of squares, so that factors into 1 minus sine squared theta. And we want to make this equal to secant theta plus tangent theta So now 1 minus sine theta is equal to cosine theta by the Pythagorean theorem, or the Pythagorean identity. Says that 1 minus sine squared theta is equal to cosine squared theta. So then we get 1 plus sine theta squared over 1 minus sine theta is cosine squared theta equals secant theta plus tangent theta squared. So now this is the same as 1 plus sine theta over cosine theta with the square on the outside because each of the individuals were squared. And then by term-wise division, we get 1 over cosine theta plus sine theta over cosine theta. And then 1 over cosine is equal to secant, and sine over cosine is tangent. And we're done. So this guy, highlighter. This guy is this guy by the identity 1 over cosine theta equals secant theta and this one is the definition of tangent, that sine over cosine is equal to tangent. And we're done. So we proved this identity now in 2 different ways. And you might be thinking, well, I liked the first way better, or I liked the second way better. And that's fine. As I mentioned in the beginning, there's always going to be more than one way to do them. In fact, there's always an infinite number of ways to do them. But having the conjugate as a tool in our toolbox will be helpful from time to time. All right, let's keep on going. So let's take example number 6 and let's turn it into a U-try. So example 6 is going to be the last U-try for this section. Alright, so to do this one, the first thing we're going to use is the Pythagorean identity. And the Pythagorean identity in this case is that sine squared theta is equal to 1 minus cosine squared theta. So then that's going to give us 1 minus in our numerator 1 minus cosine squared theta. So then the next thing we want to use is the difference of squares. So a squared minus b squared is a minus b times a plus b. So we're going to end up with 1 minus cosine theta times 1 plus cosine theta all over 1 minus cosine theta equals negative cosine theta. So then we get some reduction. So 1 minus cosine and 1 minus cosine reduce out. And then the next thing we're going to do is distribute. And simplify. So if we distribute our minus sign into our parentheses, we get 1 minus 1 minus cosine theta. Those two guys cancel out. Equals negative cosine theta. And we're done. Alright, so there are some other identities that we should be aware of, and they do come up from time to time, but as I mentioned, there's a whole bunch of trigonometric identities, and I wouldn't recommend trying to memorize all of them. You should just know how to use them. The ones that you end up using a lot, you'll memorize just by using. So the next type of identity is the product to sum identities. So this is if we have products of sines and cosines, we can turn them into sums of sines and or cosines. So let's go ahead and take a look at example number 7. So it says, excuse me, find an identity for 2 times the sine of 3 theta times the cosine of 7 theta. So if we look at our list of product to sum identities, we have sine and we have cosine. So sine, cosine, that's going to be the one we have here at number 3. So if we have sine, cosine, that means our x is going to be 3 theta, and our y is going to be 7 theta. So if we use that identity, we're going to have 2 times 1/2 times sine of 3 theta plus 7 theta, and then plus sine of 3 theta minus 7 theta. Those reduce out, and then 3 theta plus 7 theta is 10 theta. So we get the sine of 10 theta plus 3 theta minus 7 theta is the sine of negative 4 theta. And then sine is odd, so we get the sine of 10 theta minus the sine of 4 theta. And that would be our identity for this. All right. So the last one for this section. Here is a U-try for you guys. So let's go ahead and find an identity for 2 times the cosine of 5 theta cosine 4 theta. Alright, so to do this U-try, we just have to identify which one of these it's going to be. And it's going to be the second line because it's cosine times cosine. So similar to what happened before, we're going to have 2 times 1/2. And it's going to be the cosine of 5 theta plus or minus 4 theta. Helps if I look at the formula. Minus 4 theta plus cosine 5 theta plus 4 theta. So 5 theta take away 4 theta is going to be just theta. Those cancel out. So we get cos theta plus the cosine of 9 theta. So this is really just finding the appropriate identity on the sheet and executing it.